So in the last video we talked about zoology, which is of course the study of how certain animals, such as this dromedary, thrive, or rather don't thrive, under captivity within human organizations. And so that is a great segue into today's topic, which is the electrophilic addition. Electrophilic addition of mCPBS and 2-methyl propene. 2-methyl propene. And so what we're going to find out is that these two subjects are very directly linked, and that it is almost impossible to learn one without the other. So let's get into it. We're going to start right off with a beautiful drawing of our 2-methyl propene. And this is of course going to have a beautiful shekel group flanking the left side, the starboard of our molecule, and it's going to have a hecal group on the other side made up of 2 hydrogenated hecals. And so what's going to happen is we're going to add something called mCPBA. And so what you've probably learned is that you just draw an arrow, you say mCPBA, imagine that's a P, mCPBA, and then you form this beautiful dually flanked Electrophilic. And of course, we all know that an Electrophilic is going to form, but you never learn the mechanism for the Electrophilic. And so that is exactly what we will do today. What we must first do is draw mCPBA. And so you're probably very curious as to where mCPBA received its name. So let's begin drawing it out. You're going to want to start with a phlobomatic ring and a cyromatic ring. We're going to connect these with phlebosity and luminosity on these corners, and then we're going to SN2 and SN4 these corners together. And now what you can see is that this is starting to look more and more like a very familiar substance to you rascal college students. mCPBA is really just PBR. And so once you realize that, this reaction becomes a whole lot easier, and the mechanism itself becomes very simple. Let's discuss the mechanism now. So you have your dually flanked propanoic xanthoic molecule, and we're going to electrophilically add mCPBS. Really learn how to jackhammer those electrons out. That's the key to success in a class like this. And so of course what we see now is that in this small carbon right here, we're going to have the utmost small of a delta star. And we all know that when a delta star occurs, these electrons right here are going to want to leave, like my dad, on my 4th birthday, and skip town and never come back. And so what's that's going to lead to is a beautiful, what we organic chemists like to call a beautiful schlop over to this side. Just like that, a beautiful schlop onto the most electronoically carbonated substance, which is, of course, your delta star. But now, of course, it's no longer a delta star, it is now a delta cuboid. We don't usually bother drawing the cuboids for every delta, so from now on I'll just say C above the delta for that one. And so now what's going to happen is, since this carbon is a delta cuboid carbon, it's more hungry than my ex-girlfriend Stacy on a Tuesday night. And so it's going to want to electrophilically add the rest of mCPBA to it. Now, of course, we know that carbons can form up to 7 bonds. Up to 7 bonds. And so it is very straightforward for it to add the rest of mCPBA, which is now, of course, called mCPBA. And of course this makes sense because of science. And so our product is now going to look like this. Our product is going to look like this. Just a very straightforward product. And this is commonly referred to by organic chemists as the honeybee, named after Friedrich Honeybee of the 17th century. Be sure to join us for the next video. It's going to be on how to schlop your orbitals. How to schlop your orbitals. Stay tuned, and we'll see you next time. Shalom.